Hello everyone, we will continue with chapter 2. So in this section, which is section 4 in chapter 2, we will talk about rates. Okay, so rate of energy, uh, which we have heat transfer and work. So we have covered work so far. So we will talk about rate of work, which is nothing but mechanical power actually. So in terms of the notation, so how the symbols go for the rate, okay, we put a dot on top of the symbol to denote that it is the rate. Okay, so suppose the parenthesis is any kind of property. When we put a dot, it is nothing but the time derivative of that part. Okay, that's what we mean by the rate. T, lowercase t, stands for time here. So as a very basic example, okay, suppose you are given a system, whatever the system is. This is the system boundary. Okay, and we add mass as 20 kilograms, and we take out mass which is 8 kilograms. So the question is, what is the change of the mass within the system? So it's a very redundant question, it's a very basic question, but we write down the mass balance, right? So the final mass of the system minus initial mass of the system is equal to m in minus m out. This is the mass balance. The left hand side is nothing but the final mass minus initial mass, which is delta m. It is m as in mass. Okay. Oops, sorry. It's not, should not be something in red. So let me rewrite. Delta m. It is m in minus m out. M in is 20 kilograms. M out is 8 kilograms. So the difference is 12 kilograms. So in rate form, delta, by the way, the change in anything, change in any property is always final minus initial. So don't forget that. If you consider the mass balance, I give example of mass balance, but it is applicable for energy balance, entropy balance for as well. On rate basis, rate means time derivative. Okay. So delta m, this is delta, m in minus m out, right? So what we do is we divide all the terms with delta t, where delta t is the duration of process, if you wish. So in the previous example, I input like 20 kilograms, right? So if I put this in 4 seconds, the rate is nothing but 20 kilograms divided by 4 seconds, so it's 5 kilograms per second, right? So that is basically what I mean by the rate. So you write this down. This is kind of a derivation of the rate, okay? And you take the limit give me a second. You take the limit of this one as delta t goes to 0, okay? Delta m by delta t becomes, in the rate, dm by dt, time derivative of mass. This is the mass change of the system. And the right hand side, m in divided by delta t becomes m dot in. M out divided by delta t becomes m dot out. So this becomes the rate. Okay. So in this one, the units are kilograms in the mass balance. So this is the mass balance on rate basis. The units are kilograms per second. So when you see a dot, it is the rate form. It is per, sorry, that's not what I meant. It is per second. It is the rate form. Okay. So in the previous example, previous basic example, if, as I said, the delta t is 4 seconds, okay, dm by dt is 12 kilograms per 4 seconds, so that's going to be 3 kilograms per second. M dot in becomes 20 kilograms over 4 seconds, so that's going to be 5 kilograms per second. M dot out becomes similarly, that was 8 kilograms, right? Divided by 4 seconds, so it is 2 kilograms per second. So each and every second we give 5 kilograms, we take out 2 kilograms, and eventually for each and every second we increase the mass of the system as 3 kilograms. So the schematic will be something like this eventually. This is the system once again with the system boundary. In this case, I'm not asking for delta m, I'm asking for dm by dt. So for each and every second, how much mass change we have. Okay. These values are known. This is 2 kilograms per second. This is going to be 5 kilograms per second. Therefore, dm by dt, this is the mass balance in rate form, m dot in minus m dot out. So from here, dm by dt is equal to 5 kilograms per second minus 2 kilograms per second. So it's going to be 3 kilograms per second, which we found out, right, previously. So that's basically the same. In short, let me try to summarize the mass balance, and we have mass balance in the rate form. Mass balance is the masses. The change of mass is equal to m in minus m out. All the units are once again in kilograms. In the rate form, it is going to dm by dt is equal to m dot in minus m dot out. So we put dots, and the units are kilograms per second. It is rate form. So as I said, the mass balance is just an example. You can write this for the energy balance or entropy balance. And the way that this is written is, the right hand side is the rate, in this case of mass, that crosses the system boundary. Again, crosses. This part is nothing but time rate of change inside the system boundary. I emphasize inside over here. All right. So this is nothing but the rate form. This is what we mean by the rate for each and every second. So we have covered work, right? And the rate of work is what we call as the power. We sometimes omit out mechanical because we are talking about mechanical engineering, but it is very similar to the electrical power as well. So the definition of power is the rate, supposed to be rate, of energy crosses the system boundary in terms of work. So rate of work is power. Okay. The notation is W with a dot at the top, W dot. The unit is kilojoules per second, which is kilowatts, or joules per second, which is watts. Okay. And the way that you can convert one to another, so energy is nothing but the time integral of the power from time 1 to time 2. So if you, well, Suppose that you have electricity. Anyways, that's going to be an example. Suppose you have an electrical heater. It consumes 500 watts. Okay, it's rated at 500 watts. So when you plug in, for each and every second, it consumes 500 kilojoules. Okay, so if you operate this for 10 seconds, how much energy it's going to spend? So for each and every second, it's going to consume 500 joules, kilojoules, I said, right? I forgot what I said. Suppose you have 500 kilojoules, okay, of electrical kilowatts of electrical heater. Okay, for 10 seconds, it's going to be 500 times 10, so 5,000 kilojoules it's going to spend for 10 seconds. Okay, so that's how you calculate or convert from watt to joules, or from power to energy over here. Okay, so that's basically the rate. I will stop this section here. We end this section, and in the next video we will talk about the other mode of energy that crosses the system boundary, which is the heat transfer. Okay, so thank you for now. Take care. Bye bye.